So let's get started. We are doing something which can be called properties of determinants. Right, and we were in the middle of what we had shown a couple of things already. To recall, we showed where A was an n-line matrix that if A prime is obtained from A by switching two rows, then the determinant of A prime was negative the determinant of A. We also showed that if A prime is obtained from A by multiplying one row by some alpha, then the determinant of A prime is alpha times the determinant of A. And what I said we were going to do today was do the last sort of elementary row operation, right? So these first two were elementary row operations, so there's one row operation left. Is obtained from A by adding a multiple of one row onto another. Then the determinant doesn't change. The determinant is the same. Okay, so that's where we were. Okay, that's where we were. Now let me ask you a question. What are the determinants of the elementary matrices? What are the determinants of the elementary matrices? Right. Suppose you have the guy that accomplishes a switch, right? So there's three types. Remember, there's a switch type. There is a multiply a row by alpha type, and then there is a add a multiple onto another row. Right? There's three kinds. Right? So there's these three elementary matrices. Let's call them switch, multiply, and add. What's the determinant of a switch matrix? Of an elementary matrix that does a switch? Lizzie.
-1.
-1, yeah. Why?
Because the identity matrix is diagonal and everything's 1, so the determinant is 1. So then if we switch to it's -1.
Yeah. So basically, by the first fact, you know that if you take the identity matrix and you switch two rows, the determinant will switch by -1. Right? Will be multiplied by -1. Well, the determinant of the identity is 1, so the determinant of this kind is going to be -1. Right? Similarly, the determinant of this guy is going to be what? Somebody other than Lizzie say it. If you multiply by row by alpha, the matrix that accomplishes that. Molly?
It's just going to be alpha.
It'll be alpha, right? This guy will be alpha, and the last guy will just be 1. Right? And you can calculate those directly, right? You could calculate those directly if you wanted. Okay. Okay. So, like, if you have one of these, suppose you have the last type, right? Adding on alpha of the first row onto the third row, right? Adding on alpha of the first row onto the third row, that would be this matrix, right? And then you could calculate the determinant directly. It's a triangular matrix, so the determinant is just the product down the diagonals, right? So the determinant of this guy is going to be 1. Okay. Is everybody okay with those 3 facts, those 3 observations? Okay. So there's a way of rephrasing this. You can rewrite this. So you can restate this thing here. Basically, it's this: if A prime is some elementary matrix times A, then the determinant of A prime is the determinant of the elementary matrix times the determinant of A. Everybody see that? Everybody see that that's exactly the same statement as here? Right? Right? Because it just encompasses everything, right? If you've got a switch, then the determinant of the switch guy is going to be -1. That's the determinant of the switch matrix times the determinant of A. Right? If you multiply by rho by alpha, the determinant of the multiplied guy is going to be alpha times the determinant of A, and so on and so forth. Okay, so this is just a more concise way of stating the thing on the left. Okay. Any questions? Any questions? Okay. You all seem kind of down again. I'd say to this, so I teach the second class, a second section of linear algebra at 11, and I call that class the slightly more alive class. Yeah, I guess they have a 2-hour advantage. Okay. Okay, so let's go on. We haven't proven this last one, right? I said that this is the hard one, right? That when you take a multiple of one row and add it onto the last one, add it onto another row, then the determinant doesn't change. Okay, so we need to prove that. And the proof of that relies on something that we're going to call the wrong cofactor lemma. The wrong cofactor lemma. So the proof of 3 relies on something that we're going to call the wrong cofactor lemma. Okay, and here it is. If you have an n by n matrix, okay, and you consider AI1 capital AJ1 plus AI2 capital AJ2 plus AIN capital AJN. Okay, where these guys are the entries and these guys are the cofactors, as always. Right? Well, if I equals j, what do you get? If I and j are the same, you get AI1, capital AI1, AI2, capital AI2, etc., etc. What's that?
Wouldn't that just be the determinant along row I?
That's the determinant, right? Calculated along the row I. So that's the determinant of A. If I and j are the same, right? Right, by our useful theorem, right? By useful theorem. Exactly. Okay. Now, what the wrong cofactor lemma says is if you take j to be different from I, If you take j to be different from I, then something happens. Did anyone read it? Did anyone know what happens? Anybody know? No? Molly?
It just equals 0.
It equals 0. Yeah, it equals 0 if I is different from I is different from j. Okay, so if you take the cofactors from the wrong row, that's why I'm calling this the wrong cofactor lemma. Okay, if you take the cofactors from the wrong row, then you're going to get 0. Okay, right. Okay, one way of thinking about this is as a dot product, right? This is saying that the dot product AI1, AI2, AIN against AJ1, AJ2, AJN is 0 if I is not equal to j. And it's equal to, the determinant of A if I equals j. So it's a statement about perpendicularity, right? They're perpendicular to each other if I is not equal to j. Okay. So let me see if I can give you an idea of why that happens before we do the rigorous proof. Okay. So maybe the proof is kind of abstract, but once you see it concretely, you'll say, oh, that's actually pretty simple. So I'm going to just draw something small down here. Here it is. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. No. 9, 10, 11, 12, 13, 14, 15, 16. Okay. So you have some matrix there. Okay. And now what I'm going to do is I'm going to create a second matrix, A prime, where I copy one of the rows onto the other. Okay, so I'm going to copy the third row. I'm going to copy and paste the second row and paste it onto the third row. Okay. Okay. What's the determinant of A prime? What's the determinant of A prime? 0, right? Because it has two identical rows, right? And we had some theorem last time. That you have matrices that have two identical rows, then you have 0. You have a 0 determinant. Okay. So it's okay. That's not interesting. We already knew that. What is interesting is this. Take the cofactor expansion down the copied row, down the pasted row. Take the cofactor expansion of the determinant down the pasted row. Okay. Well, that's going to be 5 times the cofactor A31 plus 6 times the cofactor A32 plus 7 times the cofactor A33 plus 8 times the cofactor A34. Okay. But you see, so that tells you that this thing is 0, right? This thing is 0, right? But what is this thing? This is, if we go back to our original matrix, that is A21, A31 plus A22, A32 plus A23, A33 plus A24, A34. Right? And so you see that if you use the entries from one row, but the cofactors from the other row, you get 0. Okay? That's the proof. Okay. Now we're going to write it out. Okay. Everybody following? Right? You ask yourself, what would happen if we use the entries from this row, but the cofactors from another row? You say, okay, well, do this. And you see that if we take the expansion down this row, that's what we get. The entries from the second row of our original plus the cofactors of the third row of our original. But that's 0 because we know that if you've got two rows that are the same, that's 0. So you would get 0. Okay, so that's the proof. It's simple. Writing it out is not simple. People often get confused when you write it out, but it's actually pretty straightforward. Okay, so proof. of the wrong cofactor lemma. Okay, consider the matrix C, which is the same thing as A. So A11, A12. I'm just going to write out what we did over there, but sort of more abstractly. But this is the ith row, and this is the jth row. Right? So let's start off with our matrix, ARS. Right? You start off with one matrix. You make a new matrix where you've taken the ith row and pasted it on top of the jth row. Taken the ith row and pasted it onto the jth row. Right? So C is A with row I pasted onto row J. Okay, and then the proof is take the expansion down that row. Right? So the determinant of C is 0, since there are identical rows. The determinant of C is 0. Okay, but the determinant of C is by expansion down the jth row. That's going to be AI1, capital AI1, right? I'm sorry, capital AJ1, sorry. Right, capital AJ1 plus AI2, capital AJ2 plus AIN, capital AJN. Right? So that thing, the cofactor expansion with the wrong cofactors, equals 0. For I equals J, for I different from J. Okay. We already knew that if you took the right cofactors, you get the determinant. That's from the useful theorem. Yeah, Nico.
So you're saying that the one on the right is 0.
Yeah.
And then are you saying that the one on the left is the same as the one on the right because you're just allowed to?
I'm saying that
the row is equal to the other row.
I'm saying that this thing here can be obtained by taking a matrix and taking the expansion down the pasted row, right? Right. If I want to figure out what this number is, this is some number, right? I start off with some matrix, and I say, what would happen if I took the entries from one row, but the cofactors down a different row? Entries from the second row, cofactors from the third row. Okay. And you think of it, and you say, oh, well, actually, that's going to be the same thing as if that'll be exactly the same thing as if I took the second row and pasted it onto the third, and took the expansion of the determinant of the new matrix down the third row. Right? Because you see what happens. If I take the expansion down this row, I'm going to get 5 times the A31 cofactor.
And that's just because of how it's being crossed out each time you do that minor
right?
matrix.
I take 5 times -1 to the 3 plus 1 times the determinant of the minor. But the determinant of the minor, this minor is the same minor from over here. Right? It's the same minor. Right? So so the point is that the cofactors from here along that row are the same as the cofactors from there. right? Right, because the minors are the same. The only row that's different is this row that gets crossed off when you do them, when you calculate the minors. Right? This matrix is the same as that one, except for this row. When we do the minors, we eliminate that row anyway. So the cofactors are the same.
Can you clarify why you pasted row 2 on row 3?
So that's exactly, right, so look what happens when you paste you paste row 2 on top of row 3, right? And you say, okay, this matrix has 2 identical rows, right? So the determinant is 0, right? Okay. Now let's take the expansion let's expand the determinant by minors down that pasted row. Okay, right? We're going to get some number that's equal to 0. Okay. What do you get? You get 5 times the a through 1 cofactor plus 6 times the a through 2 cofactor, et cetera, right? But that gives you, that's exactly what that is the, if you took the expansion of the, if you took the entries from this row but the cofactors from the other row. Okay, so the reason you do it is because you're trying to calculate what this is. And you say, oh look, this thing is actually 0. This thing is the determinant of this matrix, which is 0. Yeah, read.
Wait, so we proved that that's equal to 0.
Mhm.
How does that prove our original claim that adding a multiple of one row to another doesn't change the...
We haven't gotten there yet.
Oh,
we haven't gotten
okay.
there.
I thought this was the end and I was really confused.
No.
The little black dot.
No. The black dot, I should say, at the end of the proof of the lemma. End of the proof of the lemma, not the theorem. Okay, now let's actually prove part 3. Okay, so proof of 3. Right, remember what 3 is. 3's claim was that if, and I'll rate it as B because I have it as a B in my notes. If B is obtained from A by adding a multiple of the ith row of A onto its kth row, say. Then the determinant of B equals the determinant of A. Yeah, and I feel like I maybe haven't answered your question enough.
Yeah.
Maybe come later. Come later and we'll talk. We have to. I'm afraid we have to get through with this, but come later and we'll talk. Okay. Okay. So So suppose the kth row of B. The kth row of B is C times the ith row of A plus the kth row of A. Okay. Right. So the kth row is C times the ith row. You take C times the ith row and add that onto the kth row. Okay. Observe, if we look at the cofactors, down that row, suppose we take the cofactors of the matrix down that row. What am I going to write? Those are going to be the same things as okay, I'm going to walk out and think. Everybody think for a minute. Write down something. Okay, think about it. Talk for a minute.
You see those imbalances head against the right-hand side.
Okay, what's the answer? What is it? The cofactors of B along that row are, read,
Oh, the same as the cofactors in A.
same as the cofactors of A, right? Right, because B is the same matrix as A except along the kth row, right? And when you're calculating the cofactors, right, you're going to get -1 to the k plus j times the determinant of the minor matrix for B. I mean, I'll use an n for the minor matrix of B. Okay. But that's the same thing as the minor matrix for B is the same thing as the minor matrix for A along that row, because you cross off the row that was altered, right? And so this is going to be the same thing as the cofactor for A, where n cofactor, I'm sorry, minor for B, and m is going to be minor for A. Okay. So, what are we going to do? We expand the determinant of B down the kth row, right? Just like we did last time, right? We paste onto the kth row. We're going to take the expansion down that row. Okay. What do you get? You get the determinant of B is going to be BK1, capital BK1, BK2, capital BK2, plus BKN, capital BKN. But what are the entries of B along the kth row? Remember what the kth row of B is? It's C times the ith row added onto the kth row of A. Right? C times the ith row of A added onto the kth row of A. Right? So what's BK1? Well, it's going to be C times AK1 plus, I'm sorry, C times AI1, excuse me, plus AK1, right? Whoops. What's BK2? Well, it's going to be CAI2 plus AK2. CAIN plus AKN. Right? Because the kth row of B is C times the ith row of A plus the kth row of A. Okay, let me switch these B's to A's because we already said before that the cofactors are the same. I'm going to call these guys A's, sorry. Okay, 2 points on the exam to the person who sees the punchline at this point. Zian.
You factor out CAI1 and then capital A K1 and then you add that and then plus AK1 the lowercase AK1 and then AK1 and then you do that for all the terms. And then you eventually get the wrong cofactor lemma plus the determinant of A.
Perfect. Right, exactly. You get it. Okay, right, so you see what you're going to get. You distribute, and then you group things together. Right, you're going to end up with C times AI1, AK1, AI2, AK2, blah, 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 AIN, AKN. Right, plus AK1, capital AK1 plus AK2, capital AK2 plus AKN, capital AKN. Right? But by the wrong cofactor lemma, this first thing is 0. And so you end up, this is 0 by the wrong cofactor lemma. Right? And this thing, again by the wrong cofactor lemma when you're using the right cofactors, is the determinant. That's the end of the proof of the theorem. And you see that the proof is exactly the same as in the concrete case, right? You take one row, add it onto another, get a new matrix, and then you take the expansion down that altered row, right? I'm sorry, forget what I've just said. There was no concrete case. The concrete case was for the wrong cofactor lemma. Okay, but it's sort of similar, right? You alter one row, you take the expansion down that row, and you see that you get 0. You get 0, part of it turns into 0. Any questions? Anyone form questions? Okay. So let me just run through it again, right? You take some matrix, A, you add on C times the ith row onto the kth row. Okay. You make a new matrix B. Okay. And you say, oh look, only the kth row is different for this guy. So if we look at the cofactors down that row, they're the same, right? The cofactors of A and B. You have the old matrix and the new matrix. Down that kth row, you've got the same cofactors. Now, take the expansion of the determinant of B down that altered row. What you get is this, right? What you get is this, right? You get this times the AK1 cofactor, this times the AK2 cofactor, et cetera, but then you distribute things, you just use the distributive property and regroup, And by the wrong cofactor lemma, this whole thing vanishes and you're left with the determinant. Okay, that's it. Okay. Okay, let's go on to the next part, which is much simpler. So there's a corollary of the theorem. So the theorem is this, that if E is an elementary matrix and A and by n matrix, then the determinant of EA is the same thing as the determinant of E times the determinant of A. Right? That's what we showed. That if you alter the matrix, then you multiply its determinant by the determinant of the corresponding elementary matrix. That's what we just proved. Okay? We just proved. Just proved this. Okay. So there's a corollary. It says the following, that A is invertible if and only if the determinant of A is non-zero. Okay, so this is another way of characterizing invertibility, right? We had multiple ways before, now we're adding one more. A matrix is invertible if and only if its determinant is non-zero. Okay, the matrix is invertible if and only its determinant is non-zero. Okay. Okay. And here's the proof. You say, okay, let U be the reduced row echelon form of A. Let U be the reduced row echelon form of A. Okay. If A is invertible, then U is what? If A is invertible, then its reduced row echelon form is going to be Kaki, how about you? The identity matrix, right? U is the identity matrix, right? And what you see is that then, so the determinant of U equals the determinant of A. That's to say that 1 is the determinant of EK times the determinant of EK minus 1 down to the determinant of E1 times the determinant of A. Okay. Right? Because of this fact here, right? We said that if you're taking the determinant of E times the determinant of A, you can pull one of them out, right? This is going to be the determinant of E times the determinant of everything left over. But this is the determinant of EK minus 1 times the determinant of everything left over, and you can keep on going down, right? So you work your way down to this thing here. Okay. But the determinants of elementary matrices are all non-zero, right? It was either 1 or -1 or alpha, where alpha was non-zero, right? So none of these guys is 0. They're all non-zero. That means that, right? Well, determinant of A is going to be non-zero also. Right? In fact, yeah. I mean, since we have a 1 over here, the determinant of A cannot be 0. Maybe that's the better way to say it. We don't have to worry about this. Sorry. You say, look, the product of these things is 1, so the determinant of A is non-zero. Okay. If A is not invertible, then the determinant of U is going to be 0. Right? Because if it's not invertible, you're going to end up with zeros along the last row. Remember that? You're going to end up with zeros along the last row. So the determinant of the reduced row echelon form is going to be 0. Right? But then, again, the same thing. So 0 equals determinant of these guys times the determinant of A. Okay. And here's where we need to use the fact that I sort of brought up earlier, too early. The determinants of the elementary matrices are all non-zero, so that must mean that this guy is 0. Right? These guys are all non-zero. So the only way we could get 0 is if the determinant of A is 0. So if you're invertible, your determinant is 0. If you're not invertible, your determinant is, if you're invertible, your determinant is non-zero. If you're not invertible, your determinant is 0, right? And so that proves this statement here. Right? But invertibility happens if and only if the determinant of A is non-zero. Yeah, Russ?
So just to make a comment. So this statement is also true conversely, right? So
yeah, both ways.
Yeah.
Both ways. So yeah, look at the way we proved it, right? We say if you're invertible, then the determinant is non-zero. So this is the forwards direction. Okay. Here we're actually proving the contrapositive statement. Okay, the contrapositive statement. We're saying remember, contrapositive statement is this one, right? So we're taking the contrapositive statement, which is if A is non-invertible, then the determinant of A is 0, right? And that's what we do. If A is non-invertible, then the determinant of A is 0, right? So we prove the contrapositive of the reverse direction. Right. The reverse direction, we're trying to prove the reverse direction, right, which says the determinant of A non-zero implies that A is invertible. And we prove that by contraposition. We say we're going to prove if A is not invertible, then the determinant is 0, and that's what we do. Okay, so we have proven both directions, the first and the second, the forwards and the backwards direction. Okay. So there's another theorem that sort of goes at this point, and it's this one, that the determinant of a product is the product of the determinants. But I'd like you to read it yourself, please. So read it yourself. It's not particularly, it's not particularly interesting, but we'll need this fact, so please just read it. Instead of doing that proof, let me give you an application of what we've been doing, which is the calculation of determinants. So simplifying the calculation of determinants. Okay. So somebody asks you to calculate the following determinant. It's not hard, but let me show you how you can make it easier. Okay. So you're given this thing, and you say, well, I'm going to do Gauss. So suppose this matrix is gigantic. Okay. Pretend that it's gigantic, even though it's a 3x3. Okay. You say, okay, I don't want to do the calculation. I'm going to simplify it by using elementary row operations. So what I'm going to do is Gauss-Jordan reduction, basically, or Gaussian elimination. So I'm going to say, I'm going to switch this. I'm going to switch the first and third rows, 3, 2, 0, 5, negative 2, 1. Okay. Now, when I did that, I multiplied the determinant by negative 1. So I need to keep track of that. Okay. So there's a negative 1 there. Okay. And then I say, okay, now I'm going to use the pivot here to clear out this one and this one. Right? So I'll clear out this one. I'll add negative 3 of the first row onto the second row, and that doesn't change the determinant. Remember? So that's good. Right? So I say, okay, this is the same thing as the determinant of 0, negative 1, negative 3, 5, negative 2, 1. Right? I multiplied row 1 by I added negative 3 of the first row onto the second. Right? That doesn't change the determinant. I keep on going, right? I take negative 5 of the first row and add it onto the third. 0, negative 7, negative 4. Again, that doesn't change the determinant, right? Then I multiply the second row by negative 1, right? In order to do that, I need to put a negative 1 here, right? Right? And then I multiply the second row. I add 7 copies of the second row onto the third, right? And I get this matrix. Okay. Now this is simple. It's a triangular matrix, right? It's a triangular matrix, so its determinant is 17, right? And so I didn't need to do. I didn't have to, use the definition of determinant cofactor. I didn't have to use cofactors, basically, right? I didn't have to use the recursive stuff, right? Instead, I reduce my matrix down to triangular form and just say, okay, the determinant of that is 17, and keep track of the changes I made along the way. And so you can see that this would be helpful if your matrix is huge, right? Because it's easy to do row reduction. It's computationally intensive to do the calculation of the determinant recursively. Okay, that's it for today.